Hello everyone, here's another Physics IB past paper question. This one is May 2018, standard level, paper 2, and this is question 2. So here we have a gas. We have a closed box with a fixed volume, so we know the volume, and it's containing a certain concentration of an ideal monatomic gas. This just means that we can model it as an ideal gas. We can take all those assumptions and use our PV-nRT formula to model that ideal gas. And then we're given the temperature to be 290 Kelvin. Our job here is just to calculate the pressure of the gas. So pretty straightforward. So PV-nRT we should be pretty familiar with. So pressure times the volume is going to be equal to the number of moles multiplied by a gas constant, R, and the temperature. So to find the pressure, obviously we're just going to solve for P. So it's going to be nRT over the volume. So let's go ahead and plug those numbers in, and we'll make sure we're being a good student here, and we're going to keep track of all of our units. So the mole is given to us, 3.0 moles. There we go. Multiplied by the gas constant, which is 8.314. And just to keep the units of the gas constant, it's joules over mole Kelvin, like that. And then temperature to 90 Kelvin, all divided by the volume, which is 0.15 meters cubed. So we can keep track of all of our units. So we can cancel the moles here, obviously, and we can cancel the Kelvin. So we're left with, if we actually did the calculation, put the numbers into our calculator, I think we get 48198. And if we look at what we have so far, we have joules meters cubed. So let's just put that in here, joules over meters cubed, and that doesn't really give us much sense of pressure. So let's look at these units in a bit more detail. Another way of saying a joule, if we look at our work energy theorem, is Newton times meter, divided by meters cubed here. And so hopefully you can see we can cancel this and give ourselves a square, and this is starting to look a bit like a pressure, because it's now going to be newtons, which is a force per meter square, which is a surface area. So that's the force pushing on a surface area. In fact, that there is our pascals for a pressure. So I guess if we wanted to write this out in the correct form, we could say, well, how many decimal significant digits? Well, we've got to be careful because look, we've only got two significant digits here. So I'm going to write this answer out as, and then we can talk about kilo. So 1, 2, 3. So yeah, 48 kilo and pascals, which is PA. So there we have it. Except for one last thing, just to check, of course, we've got our data sheet here. This is our PV-nRT right here. But take a look up here. This is our pressure, force over area, which, of course, is what we have here. Force in newtons over meters squared, which is area. So it's always good to keep track of our units, and unit cancellation is a really nice way to check that you've solved a problem correctly. Okay, so part B, we have this gas now being supplied with some energy, 0.86 kilojoules of energy, and we're seeing a temperature increase of 23 Kelvin. We're told the specific heat capacity of the gas, and we're asked to calculate the kilograms, the mass of the gas. Well, hopefully you can decipher this as soon as it says specific heat capacity. We're allowed to model this with our Q mc delta T, so this specific heat capacity formula, and Q, remember, is the change in energy. So let's just write these down. Q, in this case, is going to be the change in energy that we're told, 0.86 kilojoules, And what else do we have? Change in temperature. We have a delta T, which is 23 Kelvin. And we have C, which is the specific heat capacity of whatever this gas is, 3.1 kilojoules per kilogram Kelvin, or temperature, kilogram temperature. Conveniently, it's already in kilojoules. You have to be careful with specific heat capacities because often they change between kilojoules and joules. So just be careful of that. This is in kilojoules, which conveniently matches with our units for the energy change. So we're not going to need to do any changing there. Now it's just a case of plugging it into our formula. So let's go ahead and do that. The formula that I'm going to use is mc delta T, and I'm trying to find the mass. So the mass here, of course, is going to be Q over C times the change in temperature. So let's do this, just keeping track of all of our units. So I've got 0.86 kilojoules, 0.86 kilojoules is an energy change, and then that's divided by the specific heat capacity, which is 3.1 kilojoules, kilojoules over kilograms times temperature. There we go. Multiplied by the change in temperature, which is 23 Kelvin. Let's just change the temperature for Kelvin, just so that we have that as a value here. So rather than having T's, I'm going to put in Kelvin just as a unit. So Kelvin and Kelvin. That way it's going to be easy now for us to cancel out our units. So kilojoules and kilojoules cancel. Kelvin and Kelvin cancels. And this kilogram, of course, is going to come to the numerator part of our fraction, and that's going to give us kilograms. So plug those numbers into your calculator and you're going to get a mass. Let's put it here. Mass is going to be 0.01206, and the unit was kilograms. Now, keeping track of significant digits, what do I have? I have 2 and 2 and 2, so 2 significant digits. I'm going to say 0.012 kilograms. Or if we wanted to say 1.2 times 10 to the negative 2, just to keep it in kilograms. Okay, so part 2 of B is getting us to calculate the kinetic energy, or the average kinetic energy of the particles of the gas. So this is where we have that connection between thermal physics and Newtonian statistical mechanics, I guess, which is where we've derived this idea of kinetic energy being equal to the temperature, basically. There's the temperature in T. Now you just have to multiply it by Boltzmann's constant and 3/2, and you get the equivalent of 1/2 mv squared. And that's really all we're going to do. We know that the gas started with a temperature of, so the starting temperature was 290 Kelvin, and then there was a change in temperature of 23 Kelvin. So obviously the actual temperature at this point, the T, is going to be 290 plus 23, so it's 313 Kelvin. And we're trying to solve for the kinetic energy, so we're trying to get EK, and EK is 3/2 Boltzmann's constant multiplied by this temperature, which we've just calculated to be 313 Kelvin. Boltzmann's constant, let's put this in, so 3/2, and Boltzmann's constant is 1.3806, times 10 to the negative 23, and then the units, it's meters squared kilograms over seconds squared temperature. In fact, there it is. This is just a screenshot from your data sheet. I think I might have added an extra couple of sig digs, so we'll take those off. And we will also just note that the units from your data sheet are joule per temperature, or Kelvin. So I'm just going to change that as well. I'll turn the temperature to Kelvin like this. But yeah, please note that I've put these units in. This is a joule, isn't it? Kilogram meter squared over second squared. That's the joule. And so let's keep going. I'll move this up here. Of course, we need temperature, so let's put that in. So multiplied by 313 Kelvin. Let's go ahead and just cancel out these units. So Kelvin cancels with Kelvin, and there we have it. We're left with kilogram meter squared per second squared, which is in fact a joule. So we can finish this off. We can say the kinetic energy is equal to this calculation. Let's plug that into our calculator, and we end up with 6.5 times 10 to the negative 21, and that's in joules. Okay, so the last question, C, is a qualitative question. It's asking us to explain, with reference to the kinetic model of an ideal gas, how an increase in the temperature of the gas would lead to an increase in the pressure. Okay, well, let's start off just by looking at our kinetic model of the ideal gas, and that would of course be this Boltzmann formula that we just previously used. So let's just enlarge this a little bit. This is again just from our data sheet. Really what we're saying here is that if the temperature goes up, why does the pressure go up? Well, if this temperature goes up, if this T goes up, then of course what's going to happen to the kinetic energy is it's also going to go up. So the particles are going to move faster. So we can say, let's see if I can move this out of the way, we can make a statement. We can say that as the temperature goes up, you're going to get an increase in the average speed of the molecules. Increase in the average speed of molecules. And that means that those molecules, if they're in a container like this, and these molecules are moving around, they are randomly going to collide with the side. And as they do so, if they have an increase in speed, there's going to be some forces. There's a force of the molecule pushing against the container, which would of course be equal and opposite to the force of the container pushing against the molecule. Either way, what we can say is that the increase in average speed means that there's going to be an increase in the force, or we could say all the momentum. Okay, in other words, the collision with the side of a container. So increase in the force and momentum transferred, let me just move that out of the way, there we go, transferred to the walls of the container, or to the sides, or the walls, we'll say walls of container. And in addition to that, of course, because they're going faster, statistically, there is a greater chance that more of them will be hitting the sides of the wall. So let's say there's an increased frequency of collisions. Okay, and if we look over here again at our data sheet, if you increase the force, then you increase the pressure. And so that's the last piece of this. We would say, therefore, increasing pressure is because pressure is equal to the force over the area. So if the force goes up, the pressure goes up. Okay, so that's the connection. It's all from this statistical mechanics, this kinetic model of the ideal gas. Hopefully you'll recall some of the derivation of Boltzmann's equations here. They include all of these things and lots of Newtonian physics as well. Okay, that's us for question 2. I'll see you next time.